Hi class, we're on to experiment 4 of Chem 111 labs. This week is purely a molecular modeling lab. You won't need your goggles or lab coat, so you can leave those at home this week. However, you will need your modeling kits, which were sold in Gill. If you don't have one, please email your instructor as soon as possible. The modeling kits are sold for $10 cash only, please. Alright, so let's go through the concepts needed for this experiment. So as always, you should always read the introduction and throughout the entire experiment before you watch the pre-lab lecture video so it makes more sense. So after reading through the introduction and the entire experiment, the overall goal of this experiment is to learn how to draw structural formulas and Lewis dot structures by using your modeling kits. Another goal of this lab is to understand bond polarity with respect to ionic and covalent bonds. This lab has to do with chapter 5 of your textbook, so please make sure you read the appropriate sections just as indicated on your lab schedule. So sections 5.4 to section 5.6. This will help you significantly in preparing for lab. So let's go through part A of this experiment. Part A first wants you to construct molecular models. So we're going to be doing this in 3 different manners: Lewis dot structures, structural formulas, and 3D structures. So Lewis dot structures are basically electron dot formula. What you need for Lewis dot structures is you need to know the number of valence electrons for a given atom. So remember, for main group elements, the number of valence electrons is equal to your group number. In Lewis dot structures, the dots represent your valence electrons. So, for example, calcium, if you take a look at your periodic table, you're going to see that it's in group 2. Therefore, it has 2 valence electrons. So when we write the dot notation for calcium, we can write it in such manner. Let's do another example. Sulfur. Sulfur is in group 6, so therefore it has 6 valence electrons. So when we write the Lewis dot notation for sulfur, we have 1, 2, 3, 4, 5, 6. So now notice it's a little bit different than what you have for calcium. So these 2 here are what we called paired electrons. And then these 2 are what we call unpaired electrons. The goal from the Lewis dot structures is to satisfy the octet, which we went over quite extensively in chapter 4. If you need revision, please review your lecture notes on chapter 4 and read your textbook. Alright, let's go ahead and do an example. If we have NH3O, how do we draw the Lewis dot structure? Well, there are several ways which your course instructor will actually go through in lecture, but one way in the pre-lab lecture, let's go ahead and write how many dots, how many valence electrons we have for nitrogen. Nitrogen's group 5, we have 5 valence electrons. Hydrogen's group 1, we have 3 hydrogen atoms in this compound, and oxygen is group 6, so again, we have 6 valence electrons here. The total number of valence electrons in this compound, you add each of the valence electrons, and you're going to find that your total valence electrons is equal to 14 electrons. So we'll go ahead and draw this. So always put the most electronegative atom in the center. So we have the following structure, which again your course instructor will go over methods in actually drawing these structures in class. So this is one way to draw it, but you never want to just leave bonded pairs of electrons in such manner. We always show the paired electrons by a straight line. So you can leave it as that, but more correctly, you should actually draw straight lines wherever you see shared electrons, which you have here. Everything else, and excuse me, I forgot one more. Everything else you leave as dot notation. Okay? So these are two possible ways of drawing Lewis dot structures for this compounds here. So that's one goal of part A. Another goal of part A is to draw the structural formula. So when we say draw structural formula, we're basically saying change the dotted bonds. And when I say dotted bonds, this is what I mean by dotted bonds. You want to change these dotted bonds to straight lines. And if you note what we did here, so we changed our dotted bonds to straight lines, so this is the structural formula. Each pair in a structural formula, each pair of dots is equal to one line. More appropriately, this one line is called one bond, or a single bond. So each pair of dots, each pair of electrons is referred to as a single bond between two atoms. So the proper structural formula, in addition actually, for structural formulas, you should actually remove the non-bonding electron pairs. So let's go back to the structure here. These here are what we refer to non-bonding electron pairs. These between atoms are what we refer to bonding electron pairs. So you remove any non-bonding electron pairs. So for our compound here, our structural formula would simply be the following. And if you note, we actually we removed the non-bonding electron pairs. So that's the difference between these two here, between Lewis dot structures and your structural formula. Lastly, in part A, you want to draw a 3D structure. Your 3D structure, I strongly advise you to use your modeling kits to help determine which way atoms face. So let me just go through this here. So if an atom is pointing towards you in your 3D model, on paper we depict it with this triangle here. If an atom in your 3D model is pointing away from you, we depict it by using these dashed lines here. And I'm not very artistic, so my dashed lines aren't very perfect. So let me use the model and draw this 3D structure for this compound here. So if you open up your model, you're going to find this long tubing here. You're going to have to actually cut the tubing so that you can actually successfully use this. So I would advise you to cut it into equal segments, because this flexible tubing is what you're actually going to use when you start forming double bonds. And I didn't actually do a great job cutting these equally, so just do a better job than what I just did in this video here. Alright, so in lab we're going to tell you what each one of these colors are, but you can probably figure them out as well. Here we have these rigid gray lines are your bonds, so we usually use them for single bonds. Red is really anything in group 6. Green is anything that's a halogen. And then here we have black, which is usually carbon. And again, you're going to be using this in CHEM111, so please make sure you really understand and start using modeling kits so that you successfully use them. And this white single electron is really a hydrogen atom. Oh, and then we have one more, which is, we have two types here of blue models, and one here, this is flat, and then this one here is 3D. I would advise you to use the 3D one when you're working with group 5. So nitrogen's in group 5. Remember, we said the most electronegative atom goes in the center, so we have nitrogen. Here we have one single bond, and then, so this is one bond, and then one more bond over here. And then we have this bond here bonded to an oxygen, so now I'm bonding it to an oxygen. And then I have this bond bonding to a hydrogen, so notice here I have oxygen, hydrogen, excuse me, and then we have these two bonds here, they're bonded to hydrogens. Oops, you didn't really see what I was putting. This bond and that bond, they're both bonded to hydrogens. Modeling kits are also useful actually to determine the shape of your structure in terms of the Vesper theory, which we'll go over in chapter 6. So you're going to be needing modeling kits in chapter 6. So if we go back to our Lewis dot structure up here, look, we have hydrogen bond, which is this. We have another hydrogen bond, which is here. We have a single bond from nitrogen to oxygen, which is here. And then we also have a single bond from oxygen to hydrogen. Notice this right here is a lone pair of electrons, non-bonding electron pairs, which is this group. And then oxygen has two non-bonding electron pairs here, which we'll go over in the Vesper theory. So how do we actually draw this? So I'm going to hold it as if it's facing me. So how do I actually draw this? Well, we have nitrogen, and then this right here is in plane. So anything that's in plane, I draw it with a single line. This is also in plane, so I could either draw it like this, or I could draw it straight line, as so. These two hydrogens are actually in different planes, right? One is pointing towards you, one is pointing away from you. So as I mentioned up here, the one that's pointing away from me, I depict it on paper using this dashed line, and the one that's pointing towards me, I depict it on paper using this wedge here. So that's how you draw your 3D structures for the third part of part A. If you note, for part A, we're going to actually provide you guys with a worksheet to draw these out. You can do them in any order that you like. So for hydrogen peroxide, if you find it easier to draw, build your 3D model first, go ahead, then draw your structural formula, then electron dot formula, or you start with electron dot structural formula, 3D model. Do it in whatever order makes the most sense for you. We have all of part A on this worksheet, which will have plenty of copies for you in lab. And then part B is identifying an unknown compound, which your lab instructor will have. And if you notice, part A and part B add up to 14 points, and then you have a worksheet that has to do with electronegativity and bond polarity. That's another 15.5 points, and your post-lab quiz is 20 points, for a total of 50 points for this week's lab. All right, let's resume our pre-lab lecture. So that's part A. Part B is unknown molecular models. So we're going to ask you to draw the structural and electron dot formula for one of the unknown models that your instructor will provide you in lab. All right, now part C. So part C has to do with electronegativity and bond polarity. We'll discuss this in lecture, but electronegativity is basically the measure of the relative attraction that an atom has for shared electrons, and I'm going to underline that because that's key, shared electrons in a covalent bond. I'm also going to underline this because as we go through lecture, you're going to see that we have ionic bonds and covalent bonds. So this chart is from your textbook. You don't have to memorize any of these values. Values will not be given on exams. What you do need to know are the trends. So if you notice here, as we go down the periodic table, the electronegativity actually decreases. As we go across the periodic table, it increases. And if you noticed, actually, as you go diagonally across the periodic table, the electronegativity increase, with fluorine being the most electronegative atom in the periodic table. So fluorine is the most electronegative atom in the periodic table. So again, let's go over this trend. So as we go across the periodic table, the electronegativity increases across the periodic table, and as we go up the periodic table, which you'll notice here, as you go up the periodic table, the electronegativity increases going up the periodic table. Another really great rule to know is, again, you're not going to be given electronegativity values on exams, you're just going to be given your usual periodic table, but really the closer you are to fluorine, the more electronegative you are. We also have really 4 elements in the periodic table that we refer to as electron hogs. So these are the most electronegative atoms in the periodic table. These are nitrogen, chlorine, oxygen, and fluorine. One thing, again, with fluorine being the most electronegative, okay, I'm going to abbreviate electronegative as EN. One thing to note is that the closer an element is to these electron hogs, the more electronegative. The more electronegative it is. All right, so that's kind of a good rule of thumb to have. So as I mentioned, electronegativity is the measure of the relative attraction that an atom has for shared electrons in a covalent bond. So what is this actually? Why is it important? Well, because that actually ties in very nicely to bond polarity. So part C is actually a worksheet that you're going to have to do in lecture, in lab. It has to do with electronegativity and bond polarity. So bond polarity basically says that in any bond where the sharing of electrons is coming from, and the key here is coming from different atoms, there will be an electronegative difference. And once you have an electronegative difference, you'll have some degree of inequality in electron sharing. Almost think of it as ownership. You never have a 50-50 ownership unless they're the same atoms. If they're different atoms, you have different degrees of ownership, and that results in a different degree of bond polarity. And then later on in the semester, you'll see that how bond polarity actually affects properties such as melting point, boiling point, solubility, etc. So again, we'll go over this in lecture, but this is basically the main concepts that you'll need for the experiment. Please make sure you bring your textbook and your lecture notes to lab. You can actually use that in lab this week. Just on the worksheet portions, your post-lab quiz is always closed book, closed TA, closed classmates. So this chart is from your textbook. Here, if we compare electronegativity difference between the bonding atoms, we can say what type of bond you'll have. And then the covalent character and ionic character, meaning is it more covalent character or is it more ionic character? So if there's no electronegativity difference, your bond type is covalent. If you have intermediate electronegativity difference, we call that polar covalent. Here it could be nonpolar covalent, here is polar covalent. If there's a very large electronegativity difference, for example, in hydrogen chloride, so hydrogen is on one end of the spectrum, chlorine is on the other end of the spectrum, that electronegativity difference is so large that we actually refer to it as a completely ionic bond, and we're going to go through more the differences between ionic and covalent bonds in lecture. And similarly, so if you have more covalent bond type, that means your bond is increasing in covalent character. If you have more of an ionic bond, that means it increases more in ionic character. So let's do kind of an example here. So if we have our electronegativity difference, if the electronegativity difference is 0, an example of that bond could be hydrogen gas. So hydrogen gas is basically 2 hydrogen atoms with shared electrons. If we were to actually use the values, which you can use for the worksheet, that has an electronegativity difference of 0, so therefore the bond type of this molecule is a nonpolar covalent. Now if we have hydrogen chloride, as I mentioned above, so hydrogen chloride, hydrogen has an electronegativity of 2.1, chlorine is 3.0, that electronegativity difference is 0.9, so 3.0 minus 2.1. So this bond is actually what we refer to as polar covalent. And one way to depict polarity is using an arrow. So the arrow points towards the atom that's more electronegative. So you have this side pulling to that side. And then finally, if you have hydrogen fluoride, so electronegativity for hydrogen is 2.1, fluorine's the most electronegative atom. The electronegativity difference is 1.9. This is what we'll refer to as a mostly ionic bond or mostly ionic character. And we depict polarity using this arrow, and we call this arrow a dipole arrow. And again, we point it towards the electron that's, the atom that's more electronegative. So a few logistics for this experiment. As I said, bring your modeling kits. If you don't have your modeling kits, email your course instructor right away, and she will tell you where to get them from. I want you to work individually, but you can talk to classmates. You can definitely talk to your lab instructor and your TA for guidance. You may also use your lecture notes and textbook. As always, you guys only really care about your grades, so you're going to only be graded on parts A, B, and C for the lab experiment, and your post-lab quiz this week is worth 20 points. Part C is a worksheet, so it's really helpful if you actually, and this worksheet will be given to you in lab, if you read through the worksheet, because it has some interesting pointers here on how you really identify the character of the bond, mostly ionic, polar covalent, based on electronegativity difference. It also gives you electronegativity values, and you'll have to answer some questions here based on polarity, electronegativity, etc., and then also using your dipole arrow. So this worksheet again is worth 15.5 points. The molecular modeling worksheet is worth 13.5 points, and this part in the back, part B, is worth 1 point. So as always, if you have any questions, email me or your lab instructors and we'll be sure to answer them. Take care.